In this video, we'll be exploring the question, what is energy and why is it conserved? So this will be a video with mathematics in it. If that's not to your liking, I have another video looking at symmetry and conservation laws, math-free, and I would say that these two videos would complement each other. Okay, so what is energy? Well, to answer the first part, what is energy? Well, close your eyes and try and visualize energy, and you won't be able to do it. If you close your eyes and try and visualize a cat or a dog or a chair, you can probably see in your mind's eye something that would pass as a cat or a dog or a chair. And that's because cats, dogs, and chairs are nouns, they're objects. You can point to them, you can put them in a container, hopefully with air holes if it's an animal. But they're easy to imagine, A, because you've seen them before, but B, they're objects that can be described with visual references. But energy is not really a noun, it's more of a verb. And typically, if you look at the definition of energy in an introductory textbook, they'll sidestep the definition and they'll say, well, don't ask that. But if you have energy, you can do work with it. So most textbooks will say, at least introductory chemistry textbooks, will say not what it is, but what you can do with it. Energy is the capacity to do work or transfer heat. Okay, so we're not going to tell you what it is, we're just going to say what you can do with it. And that's about as good as you can do without getting really mathy, and that's usually where it's left. Okay, so I'm not interested in getting super mathy here. There will be some math, but not super mathy. But I'm catching on to this word work. So I can do work with it. And in fact, work has units of energy. So work has units of energy. So let's take a second to look a bit more at work. All right. So let's start with Newton's second law. So Newton's second law is force is mass times acceleration. So F equals ma, which equals mass times acceleration, but we're going to write acceleration in a different way. We're going to write it as a change in velocity per unit time. So change in velocity per unit time. Okay, so that's acceleration, a change in velocity per unit time. Okay, so we've got this idea of force. Now, if we imagine sorry, I had to move my chair. If we imagine what work is actually doing in terms of forces, so if we imagine what work is actually doing in terms of forces, let's say we have a distance, a total distance x, yx because it's on the x-axis. So let's say this is on the x-axis, and we'll call this distance, this overall total distance, large x. Okay. And you can imagine that we can split this distance up into a number of pieces of arbitrary length. So let's say I can chop this up into a sequence of small pieces. I could make them smaller, but I want to finish this video as soon as possible. The longer the video, the fewer people will even start to watch it. Okay, unless it's a good movie. Okay, so let's say we chop total x up into a whole number of pieces, and we'll call these pieces dx, so pieces of x, differences in x. Okay, and let's say I put an object here. So let's say I put an object here and I apply a force, and then I move the object to here and then to here because I'm pushing it, right? I'm pushing it with my finger, let's say. So I'm applying forces. I'm applying forces every time I move it a unit dx. I want to get it over here, and eventually I want to get it all the way over here. So I've got to sum over those forces. So Newton was English. I believe, I don't have my historical facts right in front of me, but 1600s, I think that's when he was around. I know there was a plague, so I think it was the 1600s. Anyway, not important. But back then, the letter S was written as a long exaggerated S. Okay, so keep that in mind. That's going to become relevant. Okay, that's just how they did it back in ye olde England in the 1600s. Okay, so if that's how they drew S, and I essentially want to sum all these forces, so we need to sum the forces. That's what we need to do. Well, that would just be the sum S of the forces. But we need to sum over a distance. We need to sum the forces over the total distance, which is the sum of the little distances. So we apply the sum, the English letter S, to the forces and to the distances, because I know that the sum of the little x's equals the big X. So the sum of the little distances is the total distance. So essentially what I have here, let's go back to the black pen. I have the sum of the forces over the sum of the little distances. Well, that's equal to the work done on the object. So we've learned that essentially work done is force times by distance. Work done is force times distance traveled. Okay, and that's reasonable. You know, if you have to move a heavy object a distance x and then you have to move the same object a distance 2x, you do twice the amount of work to move the object a distance 2x. Okay, everything hopefully sounds reasonable. And why are we bothering with work? Well, remember, we're trying to understand energy, and energy at this level is often said as the capacity to do work, and work has units of energy. So we're coming at energy from a work perspective. Okay, so that's the motivation. Okay. So let's take what we've just learned and so we had work is the sum of force times by the total distance, or the sum of the little distances. And notice we also said from Newton that F equals ma, which equals mass, where acceleration is change in velocity per change in time. Okay, so they're the two equations that we had on the first page. We are now going to sub in the force. So we're going to take force, which is this object here, and we're going to sub it in here. All right, so that's what we're going to do. So we've got work is the sum over force, where force is mass, change in velocity per change in time, times by the change in position dx. Now, for reasons that I don't have time to go into in this video, I can change the order of these two because they commute. So dv dx and dx dv mean the same thing, so I'm just going to shuffle those around. And I'm going to write that work is the sum mass dx by dt dv. Okay, so I've literally just changed the order of those two, and I get this term, dx by dt. Well, dx is change in position, dt is change in time, so I've got change in position per unit time. Well, I recognize that as a velocity. So I can again simplify this expression. So I can say that work is the sum, the mass, then I can say the velocity, change in velocity. Okay, so that equation's looking pretty straightforward so far. I've only got two variables, mass and velocity, but only one of them is changing. And I'm summing this funny English letter S, I'm summing over things that change. So look at the whole event rather than just an infinitesimal wiggle. Sums only apply to things that change, and things that depend on things that change. So the only thing that's changing here is velocity. So I have to apply the sum to velocity because that's changing. But notice that mass is not changing. So out of convenience, the sum only applies to anything on its immediate right. So we can get the mass out the way because the sum is not going to apply to it. So this is an option if you want to tidy this up, just so we can really focus on what the sum is going to apply to. Okay, now there's a rule. There's a rule that we have to know. Now the rule that we're going to use here is that when you apply a sum to any variable, let's call it x to a power n, so we apply the sum to any variable x to a power n as the variable x changes, then this is equal to x to the n plus 1 over n plus 1. So that's just the rule that we're going to live by. So it's a fundamental rule. If we apply that rule to our situation, where we've got v to the power 1 dv, that's the same as x to the n dx, then we've got work is going to be mass. So our variable x is now v. It's v to the power 1 plus 1. So v to the 1 plus 1 divided by 1 plus 1. Okay. So that's what we get. And we can clearly see now that that means that our work is mv squared over 2. Well, we know that by another name. This is kinetic energy. So is work always kinetic energy? Nope. But in this case, work has manifested itself as kinetic energy because of the boundary that I've applied to it. And kinetic energy we know is the energy of motion. And we can see here we have a velocity term acting on an object, so the velocity implies a motion. Velocity is a vector. We have a magnitude and a direction. So the motion is implied in the velocity. Okay. So that's great. We're starting to get some insights into energy. So again, just to recap where we're going, where we're headed, where we are, we're trying to figure out what energy is and why it's conserved. Okay, so let's start to, and we've got a segue now by considering a couple of laws. We've got an equation for energy. Great. It's an object, or at least an equation for motion energy, where an object has a mass and it can move. Okay, so let's consider, let's try and write an equation that summarizes conservation of energy. And then we'll see if we can see where it's coming from. So if energy is conserved, then I'm going to call it total energy. That means that the change in total energy per unit time must be 0, right? So that would be an expression for conservation of energy, where somehow kinetic energy is a certain type of energy, but energy can be converted into other types of energy. So we've got to look broadly at all types of energy, and the sum of all of them must be the same now and the same a while later, so unchanging. For the most part, in a chemistry class, and this is an introductory chemistry class, we can look at objects moving or the potential for objects to move in fields. So we can say broadly that we have two types of energy. We have kinetic energy and potential energy. There are other types of energy, but we're just going to make most use of kinetic and potential energy. We'll call that total energy, and that's what we are going to see as 0. Okay, so let's have a look. The good news is we already have kinetic energy. Let's show that the change in kinetic energy. Now, let's see what it is. The change in kinetic energy might not be 0. But whatever it is, we know from this equation that it must be the opposite of the change in potential energy, right? So we can see that if the change in kinetic energy per change in time is A, then the change in potential energy per unit time must be negative a, since a plus negative a is the only way we could get 0, right? So we already know if we do half of the problem, we can assume the other half with the opposite sign. Okay, so let's have a little go at that. It won't be too much, won't be too hard to do. So first of all, let's look at selecting the correct pen. So let's look at the change in kinetic energy. Well, that's just going to be the change per unit time in mv squared over 2. Okay, because we said kinetic energy was mv squared over 2. Now, what could possibly change with time? Well, clearly the number 2 can't change with time. And we'll assume that our object is not going to lose or gain mass per unit time, but what reasonably could change with time is the velocity. So we'll just rewrite this again, similar to the s previously. The d now, which essentially is the opposite of s, is going to apply to anything on its immediate right. So I can get this m and 2 out the way, they're constants, and I can apply the change with time to the thing that can actually change. Okay, so it's m over 2 and then the change in the velocity squared per unit time. There's a rule we're going to follow. It's called the product rule, but I don't always remember the names to rules, so you could call it the next rule, the second rule. Okay, this says that if you apply a change to a product, let's say AB, then you ignore one of these guys. So let's ignore A and let's apply the change to the second guy B. But then you have to return the favor. Now we ignore the second guy B and we apply the change to A. So this is called the product rule because it's a rule that applies to products. If we then apply the product rule here, clearly we have a product, we have VV. So we have the change in kinetic energy per change in time is our constant mass over 2. And then we have, let's ignore one V and apply the change to the second V. And let's ignore the second V and apply the change to the first V. And we can see what we have here is m over 2, and then we have 2 exact copies of the same thing. So I have 2 copies of V dV by dt. Okay. These 2's cancel, and then I look at this term here. Change in velocity per unit time. Well, we've seen that before. Change in velocity per unit time we saw earlier on. That's just acceleration. So I'll try and squeeze this on here. So this just becomes mVA. Okay, so let's rephrase what we have here. So we've just seen that the change in kinetic energy with time is equal to mass, velocity, and acceleration. Well, this immediately implies that the change in potential energy, or our prediction, that we haven't shown yet, but we predict the outcome, must be equal to minus mVA, right? So we already know what we're looking for, and therefore we know if we're doing it right, because we're saying that they sum to 0. Okay. Let's remind each other what work was. Well, first of all, no, sorry, we're looking at potential energy. I'm sorry. Potential energy. So this is what we need now. We already know change in kinetic energy. Let's see change in potential energy. Well, we know that potential energy it's not time dependent, it's location dependent, right? Is dependent on location, not time. But I want a time dependent, or I want to know the dependence of potential energy on time. Now, when we say it's not dependent on time, I don't mean it can't change with time. Clearly it can. Clearly it has to, otherwise there's no conservation of energy. But I mean it's typically not presented as a time-dependent phenomenon. So what I know about potential energy is that potential energy is minus the sum of forces that are acted on at a certain location as the location changes. So it's almost the same as work, but we saw work had a positive sign. If we go back to work, if we look at the work equation here, work is the positive sum of forces over unit distances, and potential energy by definition is the negative of that. Okay, so from this equation, can we come up with an expression that looks at the change in potential energy with time? Yeah, well, we acknowledge that F and D are opposites. So that means that if I want to get a D over here, I can just take an S and bring it over to the other side. So I can say that the change in potential energy is minus the force by dx. So I took the S that was on the right side and I took it over to the left side and I made it a D. I can now divide both sides by dx, so I can have d potential energy by dx, and that's minus force. So that's what we typically think of when we think of potential energy, right? We think that it's position sensitive, location sensitive, so depends on its location or the change in location x, and it's proportional to a negative force. Okay. So again, this is not what I want. This is what it comes, out the box looking like. But how can I get it to a time dependency? Well, we have to employ another rule. So there is another rule that we're going to use. And this is called the chain rule, because we're going to make like a long chain of things. The chain rule essentially says that if you, I'm just going to go straight to it because I'm running out of space. So if you take something that you, let's see, if you take something that you have, so we have the change in potential energy as a function of position, right? And let's say I really want it as a function of time. So I really want d potential energy over dt, but it really comes as d potential energy over dx. Well, I can just put dx here. And effectively, I'm just canceling these two, right? and I'm left with d potential energy over dt. Okay, that's effectively what I'm doing, but I notice that what I actually have by doing this, I've added this fraction. Well, this is change in position of p unit time. This is velocity, right? That's just the velocity. So if I can report what we actually have, we have change in potential energy per unit time is just a change in potential energy per unit position times by velocity. So that's what we have. Okay, so we've got our two equations now. We had the first equation a bit higher up. I'll just rewrite it a bit higher up here. I'll rewrite it again so it's all in the same eye shot. We had change in kinetic energy per unit time is MVA. Okay, so they're the two equations we had. Okay, now if we substitute in, let's get our red pen. If we look at this object here, and we can see it here. And all that object is negative force. Okay. All it is negative force, right? So I'll eventually get my act together here. Okay. So we can see that the change in total energy per unit time is the change in kinetic energy, or our argument all along, per unit time, plus the change in potential energy per unit time. Well, we can see now that this is just MVA. So it's VMA. If I factor out the V, and I factored out the V because I noticed that both terms have a V in it, right? I factored out the V because I can see there's a V over here and a V over here. So I've got VMA plus the potential energy. Well, the potential energy is just minus F and I've already factored out the V, right? Yeah, minus F by V, but I've already factored out the V. Well, we know that the minus F is just, from Newton's second law, is just minus MA. So this equals V MA, the plus hits the minus, makes it minus, and the force itself is just MA. So we can see that the change in total energy per unit time indeed is 0, as we predicted it was, as we knew it had to be, and the fact that it actually is confirms that it's sufficient to consider, at least in chemistry, when you're just pushing electrons around at least, just the kinetic and potential energy of the species involved. And that will conclude this video.